Greetings, my dear listeners. Today we will embark on an amazing journey that will begin with the simplest questions familiar to everyone. Where did everything come from? Did time have a beginning? What does nothing mean, from which everything emerged? These questions sound like they are being asked by children, but they are the basis of one of the most ambitious scientific theories of mankind, the Big Bang Theory. Imagine a clear night sky. Myriads of stars shine above you like endless islands of light in a vast ocean of darkness. Once upon a time, our ancestors looked up at this same sky, and they had no telescopes, no theories, no mathematics to explain what was happening, and yet they had the same feeling, a sense of admiration and awe. They made up myths, they drew maps of the stars, looked for answers to their destinies in space, and in every myth, in every legend, the same theme sounded. How did the world begin? Thousands of years later, we have approached this question with the most precise instruments, particle accelerators, and powerful computers. But the most striking thing is that the essence of the question remains the same. We are still trying to understand. How did everything come from nothing? How did space, time, and energy come about? And this is where our story begins, from the singularity to the first seconds of the universe's life. The Big Bang Theory is not just a set of formulas or dry facts. It is a kind of epic of science, in which ingenious discoveries, human errors, dramatic debates, and amazing insights are intertwined. Imagine that only 100 years ago, most scientists were sure that the universe is eternal and unchanging. And all of a sudden, there were people who dared to say, no, the universe had a beginning. Everything that we see around us was once in an incredibly dense hotspot, and from that point, from that tiny singularity, everything exploded one day. Space, time, matter, energy, everything came into existence in an instant. How did it sound to my colleagues? As blasphemy, as a challenge to everything familiar. But it is precisely such bold ideas that move humanity forward. It may seem, why does an ordinary person need the Big Bang Theory? Let physicists, cosmologists, and mathematicians deal with it. But in fact, this theory concerns everyone. It answers not only the question, how did it all begin, but also the question, who we are. Think about it. The atoms in your body were once part of the stars that flared up and exploded billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these things were born in the fiery bowels of the first stars. And there's something incredibly beautiful and profound about it. When you hear about the Big Bang, it's like you hear an echo of your own origin. Our conversation today will not be a dry lecture, not a set of facts from a textbook. I want you to feel the breath of this great story. We will move step by step, from ancient myths to the first mathematical equation, from the mysterious singularity to the first atoms, from chaos to harmony. Along the way, we will be accompanied by the stories of scientists who have ventured into the abyss of the unknown. Sometimes they have been laughed at, sometimes rejected, sometimes even accused of heresy. But it is thanks to them that we now know that our sky is not a fixed dome, but a story that began a long time ago and continues right now. I will ask you questions that do not need to be answered immediately. They will stay with you, they will sound somewhere inside, like the quiet ringing of a bell. After all, sometimes it is the questions, not the answers, that open up new horizons for us. So imagine this. Everything you know, everything you see, the whole world around you, once did not exist. There was no earth, no sun, not even the simplest particle. There was only... a what? Singularity? Nothing? Or something that we can't even describe in words yet? Maybe the universe has no beginning, only our inability to imagine one. Maybe the question what came before is meaningless because time itself came into existence with the Big Bang. Stop for a moment and allow these thoughts to penetrate you. This is not just science, it is a contact with the very mystery of existence. In the following chapters, we will travel back in time. We will see how ideas are born, how mankind came from myths to strict equations, how the courage of a few scientists changed the idea of all things. And when you hear about it, try to imagine yourself not just as a listener, but as a witness to this great story, because the Big Bang Theory is not somewhere out there, it is in each of us. The birth of an idea, from myths to the first equations. From time immemorial, man has wondered how the world came into being. The first answers were far from science, but close to the human soul. Ancient myths said that the universe was created by gods, that the heavens and the earth were born from the primordial ocean, that light was separated from darkness by the will of supernatural forces. And the god Ra lit the first sun. In Mesopotamia, it was believed that the world appeared from the struggle of the gods, and the blood of the defeated titans became matter. In India, they talked about a cosmic egg from which the world hatched. The ancient Greeks had chaos, a faceless void from which the first deities emerged. All these were attempts to explain the incomprehensible. But over time, man began to look for other ways of knowing. In ancient Greece, philosophers first thought about the nature of the world without the participation of the gods. Thales said that everything came from water. Anaximander assumed the existence of an epeiron, an infinite first principle. Heraclitus saw fire in the beginning of everything. Centuries passed. People built astronomical systems. Aristotle asserted that the universe was eternal and unchanging, and this idea lasted for more than 2,000 years. The world, in his opinion, had always existed and had no beginning. For most people, this seemed natural. After all, how can you imagine a moment when there was nothing? Medieval Europe inherited this idea, intertwining it with religious ideas about creation. But even here there were voices that spoke of the beginning of time and the finitude of the cosmos. In Islamic philosophy, thinkers such as Al-Ghazali argued that the world had to have a beginning, because the infinite past cannot be passed step by step. The real upheaval came when Albert Einstein created general relativity at the beginning of the 20th century. His equations described not only the motion of bodies, but also the very fabric of space and time. And that's where the amazing thing began. Einstein noticed that his equations predicted an unstable picture of the universe. It must either expand or contract. To avoid this conclusion, Einstein introduced the so-called cosmological constant, which made the universe static. He would later call it his greatest mistake. At the same time, in Russia, a young scientist, Alexander Friedmann, decided to take a bold step. He took Einstein's equations and showed that the solutions of these equations allow the universe to expand. In 1922, he published an article where he clearly pointed out, the world is not static, it is developing. His work went almost unnoticed. Einstein even wrote a short note where he called Friedmann's conclusions a mistake, but later he admitted that the Russian mathematician was right. Almost at the same time, the Belgian priest and scientist Georges Lemaitre came to a similar conclusion. He spoke of the primordial atom, the beginning of the world, when all things were at a single point. Lemaitre argued that the universe came into being as a result of a colossal explosion of this atom. The decisive argument was the observations of the astronomer Edwin Hubble. In 1929, he published data that shocked the scientific world. Galaxies are moving away from each other. The farther away a galaxy is, the faster it is moving away. This meant only one thing: the universe is expanding. If it is expanding now, it means that it was smaller in the past. If you go back in time, everything must have been at one point at some point. This was a confirmation of the ideas of Friedmann and Lemaitre. Thus, the myths of the birth of the world were transformed into rigorous calculations and observations. Deities were replaced by equations, and legends by telescopes. But the essence of the question remains the same. Where did everything come from? Now we ask it in the language of science. There is something touching in these first steps of science. We see how mankind has passed from fairy tale to formula, from image to number. But behind each formula, there is still the same ancient thirst for understanding. And if the ancient Egyptians looked at the stars and saw in them the footprints of the gods, then we look at the same stars and see in them traces of the Big Bang. So the idea of the birth of the universe has come a long way. From myths about the cosmic egg and divine will, from philosophers looking for the first principle, to mathematicians writing equations, to astronomers looking through a telescope. We have gradually approached the point that today we call the singularity, the moment when it all began. But before we go deeper, let's pause. Think about it. It took thousands of years for humanity to decide to ask the question differently. Not who created the world, but how did the world come into being? This transition is the real miracle. It is the one that opens the way for us to understand the Big Bang. The singularity, the frontier of imagination. When we say the word singularity, it's like opening the door to a realm where familiar laws no longer apply. For scientists, it's not just a textbook term, but a symbol of the ultimate human understanding. A singularity is the moment when all of space and all of time, all matter and energy, were concentrated in an infinitesimal point. What does infinitesimal point mean? Our minds are accustomed to images, a dot on paper, a spark in the dark, a grain of sand in the palm of our hand. But no comparison captures the essence. A singularity has no dimensions in the usual sense. It is a state where the density of matter tends to infinity, where gravity is so strong that the usual ideas about space are broken. But Einstein's equations break at this point. Quanta. Scientists often compare the singularity to the boundary of a map, just as travelers of past centuries drew mysterious figures of dragons on the edges of the seas and wrote, "Monsters live here." So we, having reached the moment of the Big Bang, are forced to admit the unknown is next. Quantum mechanics and string theory have become one of the key tools. They tell us that on extremely small scales, space and time are not smooth, but grainy. Different rules apply there. Maybe the singularity did not exist at all in the strict sense, but there was a transition to a different state of matter and energy. That our universe was born from the previous one, that the Big Bang is not the beginning, but only one of the cycles of the eternal cosmos. But let's imagine the classic picture for a moment. All the mass and energy of the universe are gathered in one point. The temperature is incomprehensibly high. The density tends to infinity. And in one moment, what we call the Big Bang happens. Space begins to expand. Time begins to flow. It is not like an explosion in the usual sense, where something is blown away into the surrounding space. No, here space itself appears and expands, but the explosion of space. Think of it as striking that the very idea of time has a beginning. Before the singularity, there was no yesterday and tomorrow. The question, what was before, loses its meaning because there was no before itself. It's like trying to find a point north of the North Pole. Our language is not adapted to such paradoxes, but they are the ones that open the door to philosophical speculation about the nature of reality. The history of science is full of dramatic moments related to the singularity. When Friedman and Lemaitre claimed that the universe had a beginning, many scientists thought it ridiculous. Even Einstein himself did not want to accept such a thought. For him, the idea of a singularity seemed too religious. He preferred to believe in an eternal universe, but the facts turned out to be stronger than doubts. As time passed, the evidence accumulated, and the idea of the beginning of the cosmos became no longer a hypothesis, but a recognized reality. And yet, despite the recognition, the singularity remains the Achilles heel of science. It's the point where relativity and quantum mechanics come into conflict. To understand what happened in the first trillionth of a second, you need a new physics, a unified theory of everything. Scientists call it quantum gravity. We don't know what it will look like yet, but the search continues. Loop quantum gravity, string theory, multiverse hypotheses. Maybe a singularity isn't the beginning, it's the edge of our knowledge. Just as the event horizon of a black hole hides the inner world from us, the singularity hides the mystery behind it. But the mystery doesn't scare us, it calls us. It reminds us that even in the age of supercomputers and space telescopes, we are still explorers standing on the shores of an uncharted ocean. Philosophers see the singularity as confirmation that the human mind is limited. We can build models, we can write equations, but there is always a limit where the language of mathematics turns into silence. So the singularity is the point at which science and philosophy converge. It is both a mathematical abstraction and the real basis of our origin. We can argue about its nature, but one thing is clear. Without it, there would be no galaxies, no stars, no Earth, no us. In the following chapters, we'll look beyond the horizon of the singularity. We'll see how the universe took its first steps, how particles were born, how the laws of physics emerged, and how order emerged from chaos. But it's important to keep the singularity in mind. First moments, the Planck era. When we talk about the first moments of the universe's existence, we go beyond the limits of conventional language. It is impossible to imagine a second or even a millisecond. Everything happened so quickly that we have to use a special measure of time, Planck time. This is about 10⁻⁴ to the power of a second. The epoch we are talking about was called the Planck epoch, in honor of Max Planck, one of the fathers of quantum theory. This was the moment when physics as we know it ceased to work as usual. The force of gravity was so great that its quantum properties could not be ignored. General relativity and quantum mechanics came into direct contradiction, which still remains a mystery. We do not know the exact laws that governed the universe during this period. Scientists are trying to reconstruct this picture. In the Planck epoch, the temperature was unthinkably high, over 10 to the 30th power of degrees. The energy was so dense that the usual particles could not yet exist. Space and time were subject to quantum fluctuations. At that point, the laws by which our world would live may have been born. The forces we know today, gravity, electromagnetism, the strong and weak forces, could have been combined into one universal force. Only later, as the universe cooled, did this force split into the familiar forces. Physicists like to use metaphors to bring us closer to understanding. Imagine a red-hot metal that gradually cools down and crystallizes, forming structures. The same is true of the universe. From fiery chaos were born the rules by which the cosmos will live. In this analogy, you can feel something almost artistic. From disorder arises order, from chaos harmony. But how can we know anything about such a distant and inaccessible time? The answer lies in mathematics and indirect traces. We can't look inside the Planck epoch directly, but we can build models, test them with modern particle accelerators, look for confirmation in cosmic radiation. There are hypotheses that it was during this epoch that tiny quantum fluctuations arose, which later, after the colossal expansion of the universe, turned into future galaxies. Think about it. Huge clusters of stars, planets, and eventually you and me all began their journey as microscopic fluctuations at a time when there was barely enough time to pronounce a word. Philosophers see a special meaning in this. The Planck era seems to tell us, the greatness of the world is born from insignificant seeds. Everything great begins with the infinitesimal. In this one can hear not only scientific thought, but also a metaphor for human life. Of course, we have to be honest. Our knowledge here is extremely limited. The Planck epoch is more of a frontier of science than a certain territory. But it is this boundary that draws researchers in. It holds the key to a unified theory that unifies quantum mechanics and gravity. Imagine what it would be like to stand at the edge of time. The infinite future stretches in one direction, and the point where the usual concepts of space and time do not exist in the other. And it is there, in this elusive moment, that the scenario for the entire future history of the cosmos is laid. In the following chapters, we will find out what happened next, how stability was born from this chaos, how the first particles took shape, how the cosmos appeared out of nothing, which will one day give life. The Great Inflation, Space and Expansion. After the Planck epoch, the next amazing stage in the history of the universe came inflation. In everyday life, we are used to associating this word with economics, but in cosmology, it has a completely different meaning. Inflation is a hypothesis according to which in the first moments of its existence, the universe experienced a colossal expansion. In a negligible period of time, less than a trillionth of a second, the size of the cosmos increased inconceivably many times over, like a giant balloon. This idea was born in the early 1980s by the American physicist Alan Guth. He tried to explain several mysteries that scientists studying the early universe faced. Why is the cosmos so homogeneous on large scales? Why is the temperature of the CMB the same at different points in the sky, even though these regions could not exchange information? And why does space look so flat that the curvature is almost zero? Inflation offered a simple but ingenious answer. If in the first moments the universe was expanding at an unimaginable rate, then this expansion smoothed out all the irregularities. Just as air inflating a balloon quickly makes its surface smooth, so inflation made the universe uniform and flat. Moreover, this process explained where the primary oscillations that became the seed of future galaxies came from. Imagine that you take a small piece of cloth and stretch it to the size of a continent. Every irregularity, every fold increases, becoming noticeable. In the same way, the quantum fluctuations that existed in the first moments swelled to cosmic proportions during inflation. Subsequently, they became the basis for the formation of the structure of the universe, galaxies, clusters, star systems. This theory sounds fantastic at first glance. How can space expand faster than the speed of light? But there is no contradiction in this. The laws of physics prohibit matter and information from moving faster than light within space, but they do not limit the expansion of space itself. Inflation also explained another mystery, the problem of magnetic monopoles. Theoretical physics predicted the existence of these exotic particles, but no one found them. Inflation showed that as a result of rapid expansion, such particles could simply be dispersed to such a low concentration that we no longer notice them. Of course, like any revolutionary idea, inflation caused controversy. Many scientists doubted, is it really possible to seriously assert that the universe increased billions of times in a trillionth of a second? But soon indirect evidence appeared. Data from satellites studying the CMB radiation showed that the picture of the sky perfectly coincides with the predictions of the inflationary model, exactly the way it should have turned out if... Interestingly, inflation opened the door to the idea of a multiverse. If inflation could occur not just once, but in many regions of space, then each of them could give rise to its own universe with unique laws of physics. We live in only one of these bubble universes, and beyond, there is an infinite variety of worlds. The philosophical meaning of inflation cannot be overestimated. We are used to thinking of space as something stable, majestic, and here we see an incredible dance of space, which in itself is capable of dramatic changes. Space is not just a stage for events, it is an active participant, the protagonist of this story. There is something poetic about it. The fabric of reality creates the world itself. For us, living almost 14 billion years after these events, inflation seems distant and abstract. But it is what has made what we see around us possible. Without inflation, there would be no galaxies, no stars, no planets. So the Great Inflation is a colossal expansion that determined the face of the universe. In the next moments, matter will begin to form into particles, the forces will separate, and the world will become recognizable. But it is always important to remember that it all began with this incredible breakthrough. After all, it was inflation that turned chaos into space and insignificant fluctuations into the basis of our reality. Matter and antimatter, the drama of the first particles. After inflation, the universe continued to expand and cool rapidly. Temperatures dropped, energy lost its incredible density, and the first particles began to appear in this raging ocean. It would seem that this is where the history of the entire material world begins, but there was a great drama in the way, the struggle between matter and antimatter. What is antimatter? In modern physics, every particle has a counterpart, an antiparticle. An electron has a positron and a proton has an antiproton. They are similar like reflections in a mirror, but with opposite charge properties. When a particle meets its antiparticle, they instantly annihilate each other, releasing energy in the form of photons. In the first moments after the Big Bang, particles and antiparticles were born in equal quantities. It would seem that their fate is predetermined, to meet, annihilate, and leave behind only radiation. The universe could remain an empty sea of energy without atoms, without stars and planets. This is where one of the most intriguing mysteries of cosmology arises: baryon asymmetry. Why did matter defeat antimatter? Why did the tiny fraction of particles from which our world was formed remain? Scientists believe that in the first moments, there were processes that slightly broke the symmetry. These disturbances allowed matter to survive. The difference could have been 1 part in a billion, but it was this tiny imbalance that caused that everything exists. Imagine a huge army where the forces of the two sides are almost equal. The battle lasts for a moment, and both armies disappear. But on one side there is a handful of survivors. It is this handful that later creates civilization, culture, and the whole world. In 1928, the British physicist Paul Dirac created an equation that combined quantum mechanics and special relativity. This equation predicted the existence of particles with a positive charge, like the electron. A few years later, Carl Anderson actually discovered the positron, thereby confirming Dirac's prediction, and it became clear: M. In laboratories on Earth, antimatter is created and studied, but its amount is negligible. A few atoms of antihydrogen can be produced in particle accelerators, and even they need to be held in special traps so that they do not come into contact with matter. But in the first moments of the universe's existence, there was as much antimatter as matter. But we live in a world where this symmetry is broken. Philosophers and physicists alike love to speculate about what would happen if antimatter had won. Perhaps there would have been an antipode universe where antihydrogen atoms would have formed anti-stars and anti-planets. The mystery of baryon asymmetry remains one of the greatest mysteries of modern science. Scientists look for answers in experiments, studying rare particle decay processes, trying to catch the slightest symmetry breaks. Each such result can bring us closer to understanding why we exist. After all, in a sense, all of humanity owes its appearance to a tiny disequilibrium at the very beginning. Think about it. Everything we see, mountains and oceans, cities and people, books and dreams, owes its existence to the fact that in the first moments of the universe, there was one extra particle of matter for every billion antiparticles. And so, the struggle between matter and antimatter was the first great drama of the cosmos. It was a dance of equal forces, in which victory was achieved by chance or by unknown laws that we are only beginning to comprehend. But it was this victory that made everything else possible. In the following chapters, we will see how the surviving particles began to unite, how the first nuclei were born, how the universe took on forms that we can imagine and feel. The photon epoch, a relict echo of birth. When the first particles of matter survived the dramatic battle with antimatter, the universe continued its rapid evolution. It was still incredibly hot and dense, but it was gradually cooling. During this period, light began to play a decisive role. In the early universe, photons and matter particles were tightly coupled. Electrons and protons were surrounded by a powerful stream of light, and each collision caused the photons to scatter continuously. The cosmos was like a boiling ocean of energy where light could not move freely. Imagine a fog in which it was impossible to see beyond the arm's length. This period lasted hundreds of thousands of years. The universe expanded, the temperature dropped, and gradually the photons began to lose their energy. At some point, the conditions changed. Electrons combined with protons to form the first hydrogen atoms. This process is called recombination. From that moment on, photons were able to move freely without colliding with charged particles every fraction of a second. It was then that the CMB radiation appeared, the oldest light that we can observe today. These photons still travel around the universe, retaining the imprint of the first hundreds of thousands of years of its life. In 1965, American engineers Arno Penzias and Robert Wilson were working with a radio telescope and trying to get rid of the interference. They heard a strange background noise that they couldn't get rid of. At first, they thought it was the equipment, then even the pigeon droppings inside the antenna. But the noise didn't go away. In the end, it turned out that they had accidentally detected the CMB radiation, the ancient light of the Big Bang. For this discovery, scientists received the Nobel Prize. The CMB radiation became one of the main confirmations of the Big Bang theory. It showed that the universe really had a hot and dense past. Moreover, the study of this radiation opened up a whole cosmos of information before us. The slightest fluctuations in temperature in it indicate the distribution of matter in the early universe, the very fluctuations from which galaxies later arose. Imagine seeing an old picture of a child, and you can guess from their facial features what kind of adult they will become, and it's the same with the CMB. From the picture, scientists can predict what the structure of the cosmos will look like billions of years from now. It's an amazing tool that connects the past and the future. The photon epoch has left us another philosophical legacy. It reminds us that light has always been close to matter, that it was light that first illuminated the darkness of the cosmos. In the most ancient myths of mankind, the moment of the birth of light was considered the beginning of the world. "Let there be light," said the ancient texts, and it's amazing that science, going its own way, comes to the same picture. Light was indeed a decisive element in the first centuries of the universe. Today, the CMB is studied with incredible precision. Satellites such as COBE, WMAP, and Planck have given us detailed maps of this ancient light. These maps are like celestial mosaics, where each pattern carries information about the origin of worlds. And the more closely we look at these mosaics, the clearer it becomes that simple fluctuations in temperature hide the code for the entire future universe. So the photon epoch is the time when light was the master of the cosmos. Photons dominated, matter was just beginning to take shape, and the universe was becoming transparent. This stage left us the greatest gift of all, the CMB, the ancient light that we can still see today. In the following chapters, we will learn how the first atoms began to be born on this foundation, how the chemistry of the universe came into being, and how the first stars began to glow. The first atoms, the beginning of the chemistry of the universe. When the light was released and the universe became transparent, a new stage in its evolution began, the birth of the first atoms. This process is called primary nucleosynthesis. It was then that the simplest chemical elements appeared, which became the building blocks of the future world. If in the first fractions of a second it was so high that the particles could not stay together, then after a few minutes, the conditions changed. Protons and neutrons began to combine, forming the first atomic nuclei. This was the decisive moment. The chaotic ocean of elementary particles turned into an ordered system. As a result of primary nucleosynthesis, hydrogen and helium were mainly produced. About 3/4 of the matter became hydrogen atoms, and about 1/4 became helium. In addition, traces of lithium and deuterium were formed. The other elements did not exist at that time. All the richness of chemistry, All the diversity of matter that we know appeared much later in the depths of stars. You could say that cosmic chemistry was born at that moment. The simplest atoms became the building blocks of galaxies, stars, planets, and ultimately life billions of years later. We are used to the richness of the periodic table, but in the first few minutes there were only a few cells, and yet it was from them that everything grew. Scientists call this process the Big Chemical Beginning. Interestingly, the calculations made in the middle of the 20th century coincide perfectly with the observations. The content of hydrogen and helium in the universe today confirms that nucleosynthesis did indeed happen as predicted by the Big Bang theory. This is another strong proof of the correctness of the model. But it's not just what elements came into being, it's also what didn't. If the conditions had been slightly different in the first few minutes, the temperature was higher or lower, the density was greater or less, the composition of the elements would have been completely different. Perhaps there would not have been enough hydrogen, and then the stars would not have been able to ignite, that the parameters coincided perfectly. This makes you think about fine-tuning the universe. The birth of the first atoms was not an instantaneous act, but a process that took tens of thousands of years. At first, electrons could not stably combine with nuclei due to high temperatures. Only hundreds of thousands of years later, in the era of recombination, true neutral atoms appeared. Philosophically, this stage can be seen as the moment when chaos first gave way to order. Space ceased to be just an ocean of energy and became a laboratory where the strict laws of chemistry operated. From simplicity arose complexity, from uniformity variety. There is something poetic about this. The world began to acquire individuality. Imagine looking up at the night sky and seeing billions of stars, each of which owes its light to the first atoms of hydrogen and helium, which were born almost 14 billion years ago. Every spark in the sky is an echo of primordial nucleosynthesis. And if you think about it, we ourselves are the direct heirs of that moment. Who has not gone through this ancient history? The importance of this step is also underscored by the fact that it laid the foundation for future stellar nucleosynthesis. When the first stars lit up hundreds of millions of years later, it was hydrogen and helium that fueled them. Stars converted these simple elements into heavier ones: carbon, oxygen, iron. But without the original material, there would be no starlight, no chemical diversity, and no life. Each candle on a birthday cake is a distant greeting from the first atoms. Thus, the birth of atoms was the beginning of the chemical history of the universe. Hydrogen and helium, the simplest elements, turned out to be the greatest legacy of the first minutes. It was from them that the entire cosmos grew. In the following chapters, we will see how these simple building blocks formed the first stars and galaxies, and how the real cosmic dawn began. The first star's cosmic dawn. After the birth of the first atoms, the universe was plunged into darkness for a while. Photons moved freely, but there were no sources of light. It was a long period that scientists call the cosmic dark ages. It seemed that space would forever remain cold and empty. But in the depths of this darkness, structures that would change everything gradually began to emerge. Hydrogen and helium, the main products of primordial nucleosynthesis, did not remain uniformly distributed. Slight fluctuations in density, which occurred during inflation, caused some regions to have slightly more matter than others. As time passed, the clouds grew denser. The temperature in their interiors increased, the pressure increased, and at some point, something amazing happened. Hydrogen nuclei began to merge to form helium. This process released a tremendous amount of energy. This is how the first stars were ignited. These first stars were not at all like the stars we are used to. They were much more massive and brighter. Scientists call them population 3 stars. Their mass could be hundreds of times that of the Sun, and life was very short, only a few million years. First, Their light dispelled the cosmic darkness and put an end to the Dark Ages. Second, the process of synthesizing new elements took place inside these stars. In their hot interiors, hydrogen and helium were converted into carbon, oxygen, and other elements that had not previously existed. When these giants died, they exploded as supernovae, ejecting new elements into space. Without the first stars, our universe would have remained poor and monotonous forever. It was they who created the conditions for the emergence of complex atoms, without which life is impossible. In a sense, every molecule of oxygen that we breathe owes its existence to the stars of the first generation. The history of the first stars has long been a mystery. They lived too long ago and disappeared too quickly for us to observe them directly. But their traces have been preserved in the chemical composition of subsequent generations of stars and galaxies. And modern telescopes such as James Webb are already beginning to approach the edges of the visible cosmos and record light from the most ancient eras. Philosophers and poets might say that this was the dawn of the universe. After a long night of darkness, the cosmos spoke the language of light for the first time, and this light was not just a beautiful sight. It carried the information, heat, and chemistry from which planets, seas, and people were born. There is something sublime about it. Everything we see and breathe begins with that distant dawn. Imagine what the sky would have looked like if we had been able to witness that time. Huge stars, 10 times brighter and more massive than the sun, illuminated space. Their light was dazzling, their lives were short, their deaths were grandiose. So the first stars were the key to the transition from a simple universe to a complex one. They turned darkness into light, simple elements into rich chemistry, empty space into the cradle of future worlds. Without them, there would be no galaxies, no sun, no earth, and no us. In the following chapters, we will turn to philosophical questions. What is the beginning of time? What is nothing? And can the universe have a true beginning? Philosophy of time and beginnings, what does nothing mean? When we talk about the beginning of the universe, we are inevitably confronted with philosophical questions that go far beyond physics. What does beginning mean? What does nothing mean? Could there be a moment when time did not exist? And can we even talk about what was before? These questions sound as acute as they did thousands of years ago, and there are still no definitive answers to them. The Big Bang Theory asserts that time and space arose together. This means that the question, what was before, loses its meaning. There was no time before the Big Bang, and therefore there was no before. But the human mind is designed in such a way that it is difficult for it to abandon the usual categories. We want to imagine the emptiness from which the world suddenly emerged. But this emptiness in itself is no longer nothing, but something. Philosophers have debated the beginning of the world for centuries. Aristotle believed that the universe is eternal because it is impossible to imagine its appearance from nothing. Augustine said that time began with the creation of the world, and asking what was before is as meaningless as asking what is north of the North Pole. But if time had a beginning, does that mean it must have an end? Perhaps the universe exists in cycles. It is born, it expands, it dies, and it is born again. In this case, the singularity is not an absolute beginning, but only a transition between states. What is nothing? From a scientific point of view, absolute emptiness is impossible. Even in a vacuum, there are quantum fluctuations, tiny flashes of energy that arise and disappear. Some scientists believe that the universe could have arisen from just such a quantum fluctuation. What we call nothing turns out to be a seething abyss of possibilities. For philosophy, these reflections open up a special horizon. Maybe we will never be able to fully understand the beginning because the language in which we think is created within time. We try to describe what was before it appeared, but our minds are not able to go beyond it. It is like a fish trying to imagine a world without water, because its existence is inextricably linked with the elements. And yet it is these questions that make us human. We are not satisfied with simple answers. We look beyond the obvious. The Big Bang Theory gives us a scientific description of the beginning of time, but it does not remove the deepest questions. What is the source of the laws of physics themselves? Why does something exist and not nothing? These questions are outside the scope of science, but they are what give it its power. Imagine a moment of silence, no space, no time, no movement. And suddenly there is a flash, and everything begins. Can you imagine something more amazing? And isn't that the poetry of science, trying to describe in words something that is almost impossible to imagine? The philosophy of time teaches us humility. We understand that our knowledge is limited, that there is mystery beyond the equations. But this mystery should not be frightening. On the contrary, it is inspiring. It makes science not only an inquiry, but also a journey to the very heart of being. So the question of the beginning of time and of nothing remains open. We can describe the first seconds after the Big Bang, but we can't answer why it happened. And perhaps this is the greatest lesson. The universe will always contain a mystery that calls us to search further. In the following chapters, we will turn to modern discoveries that expand the boundaries of knowledge and see if where new telescopes and theories are leading us. Modern horizons, telescopes, multiverses, dark energy. Today, nearly 14 billion years after the Big Bang, humanity is armed with tools that allow us to peer into the farthest reaches of the cosmos. We look back billions of years to the boundaries of the observable universe and ask new questions. If the Big Bang Theory explains the beginning, what do modern observations tell us about its future and hidden mysteries? One of the greatest achievements of science is space telescopes. Hubble has given us a grandiose picture of distant galaxies, showing us how vast and diverse the cosmos is. Its successor, the James Webb Telescope, has looked even further. It is able to capture light that has been traveling to us almost since the birth of the first stars. Each of its images is not just a photograph, but a journey through time, as they were billions of years ago. These observations confirm and deepen the Big Bang Theory. We see young galaxies that formed shortly after a cosmic dawn. We see how the structure of the universe evolved, but along with the answers, new mysteries arise. One of the most intriguing is dark matter. We know that galaxies rotate too fast to be held together by visible matter alone, so there's an invisible substance that creates extra gravity, which we call dark matter, which is 5 times more abundant than the normal matter that stars, planets, and ourselves are made of. What's it? Even more puzzling is dark energy. At the end of the 20th century, astronomers discovered that the universe is not just expanding, it's accelerating. Something is accelerating the cosmos, like an invisible force that resists gravity. We've called it dark energy, which is now estimated to make up almost 3/4 of the universe's content, which means that we understand only a small part of reality. Everything else remains a mystery. Modern theories go even further. Some physicists suggest that our universe is just one of many. The idea of a multiverse sounds bold, but it stems from an inflationary model. If inflation could occur in different regions of space, then each region could give rise to its own universe with its own laws of physics. And matter is folded into other forms. We cannot yet verify this hypothesis. And yet the idea of a multiverse is fascinating. It expands the horizons not only of science, but also of philosophy. If there are infinitely many worlds, then what does our life mean? Can there be an infinite number of copies of ourselves living in other realities? Or is each world unique and inimitable? The modern horizons of cosmology remind us that knowledge has no end. We discover the CMB, we think we understand everything, and then the mystery of dark matter appears. We explain the evolution of stars, and then dark energy arises. Philosophically, it's like an endless staircase. We climb higher and higher, and each step opens up a new horizon. But the summit is not visible, and maybe there is none at all. But that's what makes the journey so exciting. Today, humanity is on the verge of new discoveries. The telescopes of the future will be even more powerful. Private companies are launching new missions. Particle accelerators continue to search for traces of dark matter. And all this is not for the sake of abstract science, but to understand who we are and where we came from. So, modern cosmology has opened up new horizons for us. Dark matter, dark energy, the multiverse. These concepts sound like science fiction, but they are real in the sense that they help explain the observed picture of the world. In the next chapter, we will try to look at all this through the lens of a human being. What does the knowledge of the Big Bang mean to us? How does it change our perception of life and ourselves? Man and space, what the discovery of the Big Bang means for us. The science of the Big Bang is not just about dry calculations and complex formulas. It's a story that concerns all of us, because when we talk about the beginning of the universe, we're inevitably talking about our own beginning, about what it means to be a human being in a vast cosmos. When we learn that the atoms in our bodies were once part of the stars, we begin to look at the world differently. The iron in our blood was created in the bowels of ancient stars that died billions of years ago. The calcium in the bones, the oxygen in the lungs, are all the result of cosmic processes. The discovery of the Big Bang showed that the world has a history. Everything we see has never existed, but it has evolved and evolved a long way. It changes our perception of time itself. We become part of a great river that began 13.8 billion years ago and is still flowing today. Philosophers often say that knowledge of beginnings makes life more meaningful because we understand that we are not an accident, but the result of a long journey. From quantum fluctuations to stars, from stars to planets, from planets to life, this is the chain in which we take our place. And there is not only science in this, but poetry as well. The discovery of the Big Bang has also influenced culture. Artists, writers, musicians are inspired by cosmic themes. Paintings depicting galaxies and nebulae, poems about the birth of light, music reminiscent of the noise of the CMB. All this is a reflection of the fact that the cosmos has become part of our inner reality. But in addition to inspiration, the Big Bang theory is also challenging. It makes us think about the fragility of our world. After all, we understand that everything that exists has arisen due to a delicate balance of the laws of nature. The slightest change in the beginning could make the universe uninhabitable. This knowledge should awaken in us responsibility for the planet, for the future, for ourselves. For some people, cosmology becomes a source of spirituality, not in a religious sense, but in a sense of connection to something bigger. When we look at the night sky, we realize that these are not just beautiful lights, but a story that began billions of years ago, and we are part of it. It gives us strength and comfort. Even when life seems difficult, we can say to ourselves, I am a part of the universe, a part of its great path. For others, knowledge of the Big Bang is an incentive to explore. People send telescopes into space, build particle accelerators, create new theories, all in order to get closer to the truth. And this thirst for truth is part and parcel of human nature. Think how amazing it is. A small being on a small planet can talk about the birth of the universe. We are fragile and mortal, but we are able to comprehend the infinite. That makes us special. And perhaps that's the main point of the discovery of the Big Bang, that it shows that the human mind can touch the very beginning of everything. So the Big Bang theory is not just a scientific model, it's a mirror in which we see ourselves. It reminds us that we're connected to the stars, that our lives have a cosmic dimension, and even though we're only alive for a moment, we're woven into a billion-year history. In the next and final chapter, we'll take a look at the whole journey, from the singularity to ourselves. Conclusion: we are the children of the stars. Our journey has come to an end. We have gone from the mysterious singularity to the first atoms, from the dark ages to the cosmic dawn, from philosophical questions to the modern horizons of science. And now, in retrospect, what does this whole story mean to us? What place does man occupy in the vast cosmos? The Big Bang Theory is not just about explaining how the universe came to be. It's a story about us, because every atom in our body is connected to ancient events. We're made of hydrogen, which was born in the first minutes of the world's existence. We breathe oxygen created in the depths of stars. We walk on an Earth where every grain of dust was once part of a supernova. It is of cosmic origin. Carl Sagan once said, "We are made of stellar matter." That phrase has become almost a catchphrase, but its power lies in the fact that it is literally true. We are the direct heirs of the Big Bang and the stellar processes. We have the memory of the beginning imprinted in every cell, in every atom. The conclusion of this story should not sound like a period, but rather like a breath. We understand that the universe is not a static object, but a process. It was born, it evolves, and it changes. And we are part of this process. Our life is short, but it is woven into the eternity of the cosmos. We are a thread in a huge canvas, the pattern of which has been formed for billions of years. Philosophically, this discovery gives us both humility and greatness. Humility because we see how small we are compared to the universe. Greatness because we are able to understand it. We combine cosmic fragility and the power of reason. We are the only known beings who can be aware of the origin of the world and ask questions about its meaning. The conclusion of this story is also a call to accountability. We live on a small planet, fragile and unique. If our entire existence is due to the miracle of fine-tuning, then we must cherish this gift. We are children of the stars, but we must take care of the earth, our home. Imagine that you are looking at the night sky again. Now these stars are not just beautiful lights for you. Each of them is a witness to ancient history. Each of them holds the memory of the processes that once gave birth to us. When you see the stars, you see your past, and this past is majestic. So the story of the Big Bang is the story of the birth of the cosmos, but at the same time the story of the birth of us. From the singularity to the first seconds, from chaos to harmony, from the stars to man, it is a chain that connects all things. And when we become aware of this chain, we begin to look at life differently. We understand that our existence is not an accident, but part of the great history of the universe. In concluding this journey, I want to leave you with the thought: each of us carries a piece of the starry sky within us. We are children of space, children of the Big Bang, children of the stars. And perhaps the most important thing we can do is not forget this. Look up at the sky, remember our origins, and keep looking for answers, because that's our human nature.